So hello dear students. So this time we are going to discuss the next part of the EPI paradox and Bell's theorem, and we are going to discuss the derivation of the Bell's inequality, and we will also see how it is violated through quantum mechanical predictions. So that is what we are going to do in this particular video, and we will use the assumption of a local hidden variable theory, which will be included in the derivation of Bell's inequality. So Bell in 1964 formulated a theorem on an sort of an inequality, and that was based on certain assumptions related to the hidden variable nature of quantum mechanics. That is, if quantum mechanics is incomplete and there is some hidden variable element present in it, so that is arbitrarily included in the derivation for the Bell's inequality, and seen after the inclusion of those hidden variables, what results one get, they are in clear-cut violation with the quantum mechanical predictions, the actual quantum mechanical predictions that we observe. So that would mean that somewhere, whatever local hidden variable theories, if they are possible and if they are included uh, in the formalism, then what happens is they somehow violate the predictions. And so what one concludes from here is that a hidden variable theory, a local kind of hidden variable theory, has to be excluded from the view as far as quantum mechanics is concerned. So let us start with the derivation of Bell's inequality. So uh, he starts with a singlet state, that is, there are two spins. Basically there are two particles, with one with spin up and the other with spin down, and they are entangled states. So the state is something like this: psi, which is basically 1 by under root 2, and then you have an up state of particle 1 and down state for particle 2, and then minus the down state for particle 1 and up state for particle 2. So it's a spin singlet state, and it's an entangled state. And then let us say there are two observers, Alice and Bob, and then Alice measures the spin along direction A, and its outcome is given by A, capital A, which is a function of the vector small a and lambda, and Bob measures the spin along the direction B, and the outcome of Bob is written as capital B, which is a function of the direction B and lambda. And of course, these spins can only have value plus or minus 1. So capital A can take value plus 1 or minus 1, and capital B can take value plus 1 and minus 1. And lambda represents all hidden variables. So let us assume that it's always possible to include as many hidden variables as possible, but let us assume that all of them are represented by one single letter, that is lambda, and it's a single parameter. For simplicity, to start with, we just say it's a single parameter. So then Bell includes the hidden variable assumption in his formalism, and what he does is, the first thing that he do is the assumption of determinism. And what he says is that outcome of any measurement is going to be a deterministic function. That is, if we measure the spin along A and the spin along B, so if there is a hidden variable theory which basically makes quantum mechanics deterministic, then the basically outcome of any experiment, let us say if it is a spin which is measured in the direction A, then it only will depend on the direction A and the value of the hidden variable lambda, and nothing else. So simply stated, the outcome A, capital A, is just a function of the direction A and lambda, and outcome B is the function of the direction small b and lambda. And of course, A and B can take values plus and minus 1. So there is no possibility of any quantum randomness. The second assumption is of the locality. That is, Alice's outcome depends only on her settings. That is, if Alice has a setting in the direction A and lambda is the value of the hidden parameter, then the value of the outcome capital A will only depend upon direction A and lambda and nothing else. So only on the settings of Alice it will depend. Similarly, uh, B's outcome or Bob's outcome is going to be dependent upon the settings of Bob, that is the direction that he chooses, which is B, and the value of the hidden variable. So then these are the two assumptions which would be included when we include the basic criteria for a hidden variable theory, which would make quantum mechanics deterministic. Then, of course, the hidden variable lambda has got a probability distribution. So let us say let's say a pion, it actually disintegrates into an electron and positron, then each particular disintegration is going to have a different value of lambda. So the lambda changes with each disintegration of pions. So you have a large number of pions, and one after another your pions are getting disintegrated. So at each instance, let us say some value of lambda is there. For one particular disintegration, we have one value of lambda. And so there is a probability distribution such that rho of lambda, which is the probability of lambda, and then if you integrate it for all values of lambda, then you will get 1. So it's a normalized probability distribution. Then we come to the Bell's inequality derivation. So let us start with step 1. So we have a correlation function. So let us define a correlation function E, which is a function of the direction A and B, and it is basically the expectation value of all the outcomes, of product of all the outcomes for Alice and Bob. So it's just an expectation value. So you just multiply A, B, the product of A, B with the probability distribution function and then integrate it over all values of lambda. Then you will get the expectation value of the product. And since this is called the ensemble average over all possible hidden variable values, then we start with three values or three directions A, B, C. So there are basically three directions that we consider. And since for any fixed value of lambda, A and B are either plus 1 or minus 1, then A into B minus A into B, where A is basically along direction A, B is along direction B, minus A along direction A and B along direction C. So you can take common A out, and what you get is A along direction A, and then in the bracket you have B along direction B minus B along direction C. So now you know that since A along direction A is either plus 1 or minus 1, then you can conclude that B along direction B and minus B along direction C, the absolute value is less than or equal to 2. This you can conclude, as you can see from here. From this equation, you can get this identity that B, absolute value of B from direction B minus B from direction C, the absolute value of this difference will be less than 2. Okay? So then, that you can also see, since B also is plus minus 1, so B at direction B minus B as direction C can maximum take value 2 and minimum value it can take is minus 2. So the absolute value of B at direction B minus B at direction C has to be less than or equal to 2. And then from the previous equation that we had here, you can conclude that the absolute value here, which is represented here, is less than the absolute value of B, the difference in B. Okay, so you can understand this particular statement. Basically, it's just the taking the absolute values. If you have this equation here that we have just seen, and then you take the absolute values on both the sides and putting this constraint here, you will get this equation. Then, of course, we can rearrange it. Okay, so we try to rearrange it and we can get this. Okay, here it is not the absolute value. So let me just correct it. So here it is not the absolute value but the actual value. Okay, so then once you have this, so just after rearrangement you are going to get this thing. So since B can take value plus 1 and minus 1, so we have the absolute value of B in direction B minus B in direction C. The measurement of Bob in direction B minus the measurement of Bob in direction C is, of course, can be rewritten like this and then like this. So one can write it like this and then you can check it. Since if B at B and B at C are having the same value, then the absolute value is also 0 and 1 minus B at B times B at C is also 0. And otherwise also if they are different, then also you can match on both the sides, you will get the same answer. So once you have this, you can easily see that the absolute value of Bob's measurement in direction B minus Bob's measurement in direction C is just equal to 1 minus Bob's measurement in direction B into Bob's measurement in direction C. So let us go ahead from here. Then, of course, what we can do after that is we can take the ensemble average. So you just have to multiply it by lambda and take the integral over all values of lambda. So from this previous condition that we have here, we are just taking the integration, and that is what we are doing is we are just integrating for all values of lambda after multiplying it with the probability density, and we are taking this throughout the equation. That integration is done throughout this inequality. So we get this particular equation, and here I have to complete this. Here it is B at direction B lambda times B in direction C lambda. Okay, so this is what we get here after taking the ensemble average and then simplifying. Since you know that B in direction B in direction C lambda is going to be minus of the value of A or the Alice's measurement in direction C. Okay, so because Bob's measurement and the Alice's measurement are correlated, so if Bob's measurement is plus 1 in one particular direction, then Alice's measurement will be in the opposite direction. So that is why this is, so you can see from here, this particular thing is EAB and this particular thing is EAC, and this is 1 plus EBC. So it's like this. So this particular section is this here. So here we get this inequality. So finally we get this inequality. After rearrangement, we get something like this. That is EAB minus EAC is less than or equal to 1 plus EAB, 1 plus EBC. So, okay. So this is the original Bell's inequality, and it can be reinstated or restated in different terms like this one. But basically we have this identity here, which is the original Bell's inequality. And then you can see from here, let us say if you know in a singlet state, uh, uh, always if we are measuring, let us say, one spin in direction A and the other spin in direction B, then the correlation function EAB is always going to be equal to minus A dot B. So it's going to be like this for a singlet state that you can do as an exercise. So then what will happen? Let us say we have three basically angles or three basic directions here. So you have A here, this is A, this is C, and this is B. So this is 90 degrees, this is 45 degrees, and this is also 45 degrees. Okay. So then what will happen? EAB is of course 0 because it is 90 degrees. So we can write it as 0 here. What about EAC? Since A and C is 45 degrees, so it is minus of EAC is minus A dot B, so it is 0 minus of minus 0.7 something. Okay, you can say, of course, this is the cos theta cos 45 is 0.7 something. Then it has to be less than 1 plus EBC. So EBC is also 45 degrees. So it is 1 plus then minus of 0.7 because EAB or EEC, let's say, because you can say EBC is also equal to minus B dot C. So again you have this thing, and you can see from here that this inequality is violated from the quantum mechanical conclusions that we have. These are the conclusions for the singlet state that we have from quantum mechanics, and we see that this leads to 0.7 something is less than or equal to 1 minus 0.7 something. So this is not true. So this is violated. So, but this is what it is predicted by the Bell's theorem. And so you can see that the quantum mechanics are actually predicting something which is not there. If we assume a hidden variable nature of quantum mechanics and we implement that hidden variable nature, then this inequality is straightforwardly violated by simple arrangements of our detectors of the spin in these three different directions. Okay. So that's the geometric interpretation where we say alpha is the angle between A and B, beta is the angle between B and C, and gamma is the angle between C and A. That we have already seen. And then later on, these three people, Clauser, Horn, Shimon, and Holt, so they again formulated a different, you can say, variation of the Bell's inequality that is called the CHSH formulation. And they did it in 1969. And what they did was that Ellis can measure one of the two observables, A0 or A1. Okay, so he can measure one of the two observables. Bob can measure one of the two observables B0 and B1. So basically Alice and Bob now are not measuring one observable, they are observing two observables. They can measure either one of those two observables, and each measurement of course will yield an outcome plus or minus 1. So then the CHSH inequality in the original form is that this particular term here, that is the expectation value of A naught B naught plus expectation value of A naught B1 plus the expectation value of A1 B naught minus A1 expectation value of A1 B1 is always going to be less than or equal to 2. So this is a variation of the Bell's theorem, and the expectation value aibj is basically the product of Alice measurement with the setting I and Bob's measurement with setting j. So let us let us talk about this for a while. So four measurement choices are there. A naught and A1 can have either values plus 1 or minus 1. Similarly, B naught and B1 can have values plus 1 or minus 1. So then if we put this, basically all these terms, they can have values minus 4, minus 2, 0, 2 and 4, because A naught B naught can be plus 1, A naught B1 can be plus 1, A1 B naught can be plus 1, and A1 B1 can be minus 1. It is possible. So the maximum value is basically 4 here, which is 1 plus 1 plus 1 minus of minus 1, which is 4. But if we just actually do the calculation, let us say we take A1 and A0 as equal, then in that case, the value of the S term is A0 minus B0 plus B1 minus B0, which is basically going to be equal to A naught B naught, which is less than or equal to minus 1. So by taking various different combinations, you can arrive at that the maximum value that S can take is actually 2 and not 4. So you can always take all possible values, plus 1 and minus 1 for A, and plus 1 and minus 1 for B, and then of course you can all the possible combination you can put together, and you will find that the maximum value of this algebraic sum, as you can say, is never going to exceed 2. So then we just take the expectation value by putting in the local hidden variable constraint, and then we just when we are taking the expectation value, then we are going to calculate, we are going to take the outcome of A naught and B naught and so on, A naught B1, A1 B naught and minus A1 B1, and then multiply it by the probability density rho and integrate it over all values of lambda to get the expectation value of S. And then, as I said, this, as we have earlier proved or earlier shown, this S, the expectation value of S will always be less than or equal to 2. That is the CHSH inequality. So now let us go for the quantum mechanical predictions here also, again in the case of CHSH inequality. So what happens, we take the singlet state for two spin half particles, one in spin up, the other in spin down, and we interchange it and subtract from one from the other. Then what will happen, Alice measurement AI is the measurement of spin 1 of the first particle in the ni direction, and Bob measures Bj in spin, it's a spin 2 basically of the second particle and in the direction mj. So mj and ni are the unit vectors in direction I and j. So of course for the singlet state, as we have already said, that the correlation function is the minus of the dot product of the two direction vectors. So it's minus ni dot mj. This is the fundamental results from spin entanglement correlation from quantum mechanics, as can be checked by using the entangled wave function that we have. So let us say what we now do is we take uh, n naught at angle 0. So we have here n naught. This is n naught. This is at angle 0. And n1 at 45 degrees. It is at 45 degrees. Then m naught is at angle 22.5 degrees. So this is at angle 22.5 degrees. This is m naught. And then m1 is at angle 22.5 degrees, and that is in the opposite direction from n naught here, and so this is m1. Okay, so then if you just do these things, you do the calculation, you will find that the expectation value of s, you just have to take the s, the cos theta, that is the value of cos 45, cos 22.5 and cos 67.5, and those cos values you take, you just put them together and calculate the value of s. Then you will find the value of s, the expectation value of s is 2 root 2, which is 2.822. And this is the expectation value that we find from the quantum mechanical predictions. And the actual, from the hidden variable theory, the bound for the S was 2. So you can see that the local hidden variable bound, which is 2, and the ratio of the quantum mechanical expectation value with the local hidden variable bound is 2 root 2 divided by 2, which is root 2. So basically you can see that it is 1.414. So it is violated by a very high extreme, almost by the 41.4% violation is seen here. So again you can see that the CHSH inequalities are also violated. It is straightforward. You can use the quantum mechanical predictions, and from there it has been seen that what is basically ascertained from the hidden variable theory or the local hidden variable theory has not been confirmed by the quantum mechanical predictions. So then in 1987, this gentleman, Tsirelson, he proposed a bound, and then he said that for any quantum state and any projective measurement in any quantum state, the value of the CHSH operator can maximum be 2 root 2. It can never be greater than 2 root 2, but it will never be, it can always be greater than 2, which is the bound that one gets from the local hidden variable theory. But otherwise, it can never exceed 2 root 2. And he gave a proof of this using the commutation properties of the Pauli matrices and the properties of the quantum operators. And from there, he was able to prove in 1987 that the maximum value of S is, of course, 2 root 2, but it is greater than 2. So, some way or the other, it is being, the CHSH inequalities are violated.